have a look at the quiz we wrote today, quiz number 13. Question number 1, a 15 centimeter metal rod. Hey, we talk about this every single day, right? When we see centimeters, we want to circle that. We want to draw attention to that so that we don't forget to convert that to meters later on when we're doing our work. It also has a mass of 50 grams. We want to circle that one as well. Well, it's perpendicular to an external magnetic field. We like that word perpendicular because it tells us we know what to do. It tells us that what we've learned applies here. The hand rule for deflection, the FC is equal to FM, the FM is equal to QVB, FM is equal to ILB, depending upon whether it's a charge or a wire, and so on. All that stuff is applicable here. The current necessary to counteract the gravitational force. What are they really asking me there? What are they asking of me, or what are they telling me in this case when we're trying to counteract the gravitational force? We've seen this a number of times now, especially over the last couple weeks, right? But even before that in Unit 2 when we were dealing with electric forces. If we're counteracting gravity, we're balancing gravity, we're hovering, we're suspending, we're something like that that means FM or whatever force you're dealing with, whether it's electric or magnetic, in this case magnetic force, is equal to the gravitational force. So we're going to say FM, ILB, in this case because it's a wire, is equal to M times G. We're going to solve for the, what are we solving for here? The current. So let's rearrange it to solve for I. It becomes mg over L times B. When we plug in our numbers here with the correct units, 0.15 meters, 0.05 kilograms, we end up getting an answer of 6.5 amps, which of course means C is our answer there. Question number 2. The X represents a wire lying between two external magnets carrying an electron current into the page. It's an electron current, and you know what? 99% of the time when you're dealing with a wire, it will be an electron current. You guys saw once in your little mini assignment that you handed in today, conventional current. It is possible that you'll see that again, but most times it's electron current. If it's electron current, we use our left hand. If it's conventional current, we use our right hand, right? The flow of electrons versus the flow of positive. So this is electrons as it usually is. Thumb goes into the page, fingers go in the direction of the magnetic field, which of course goes from north to south. So we're going to say thumb, fingers, palm's going to point upwards towards the top of the page. So my answer for number 2 is going to be C. 3. Two parallel wires, A and B, carry currents in the same direction. Now, we're going to assume this is electron current. By rights, we should have said electron current, but if it doesn't say otherwise, it's pretty safe to assume that we are dealing with electron current. We want to find in that position Y, that position right in the middle there, what the direction of the magnetic field is caused by wire A, and what the direction of the magnetic field is caused by wire B. So let's pretend this pen right now that I'm holding in my hand is wire A. Okay, it's pointing to the right. I want to find the direction of the magnetic field directly below wire A. So I'm going to say thumb in the direction of the particle, which is towards the right side of the page, fingers bent in the direction of the magnetic field. Right now they're underneath that wire, below that wire, and they're pointing out of the page. So due to wire A, they're pointing out of the page. What about due to wire B? Well, now let's pretend my pen is wire B. Okay, thumb in the direction of the particle, fingers field. Now I want my fingers above wire B. They're pointing into the page. So wire A, out of the page. Wire B is going to be into the page. The answer is going to be C. C again. Hey, quick question for you. Before we move on, this wasn't asked on the quiz, so it's okay if you don't know the answer to this question. But I'm going to ask it anyways to see what we can do with it. What if I said here, wire A and B both produce a magnetic field, right? If there's two magnetic fields and they're close enough together, they're going to interact with each other, right? They're going to either attract or repel. These two wires will either attract or they're going to repel as a result of these two magnetic fields caused by A and B. Which is it? Are they going to attract or repel? Anybody have an answer? With some reasoning as opposed to just, you know what, I'm going to make a 50-50 guess. Cool? No? We could do it just by looking at this diagram, but I'll tell you what, there's an easier diagram to draw to determine this. I'm going to pretend that these two wires are not going, the currents are not going to the right, rather they're going into the page. So instead of looking at it from the front, I'm going to turn my head kind of around this way and look at them going away from me. Does that make sense? If I'm looking at them going away from me, then the currents will look more like this. And the magnetic fields will look more like this. It's easier to see the magnetic fields when we've got the current going away from us or towards us. So that's why I want to do that. Thumb's going to go in the direction of the current, fingers in the magnetic field. The field in both cases is going to point counterclockwise. Now, watch carefully what I want to do here. I'm going to pretend that this magnetic field is caused by a little mini bar magnet. It's not. It's caused by a moving charge. But we're going to pretend it's a bar magnet. If it is, then this would be the north pole of that bar magnet. This would be the south pole, right? The magnetic field leaves the north pole and goes back to the south pole, outside the magnet, and then inside the magnet it goes from south to north. Does that make sense? So it's not caused by that, but I'm going to pretend that it is caused by that for a second. I'm going to do the same thing with the second one. This would be north, this would be south. Can you tell me now whether these two wires that are pretending are magnets would attract or repel? Yep. Why would you say they attract, Parker? Right. You got a south pole and a north pole. They're going to attract each other. Done. Now, what if you hadn't drawn this diagram? What if you had a thought to draw this diagram, but you drew the magnets, our little pretend magnets, down here instead of up at the top? It's okay, because in the end, there's a magnetic field down at the bottom as well. Well, in that case, this would be north and this would be south. This would be south and this would be north. Look, it's still opposites attracting, right? What if we had drawn them right here? Well, this would be north and this would be south. This would be south and this would be north. Look, it's still north against south. And it's still north against south. So any way you look at it, these two wires, if the current's going in the same direction, are going to attract each other. Does that make sense? I'm not asking you to remember that if two wires have current going in the same direction, that they're going to attract each other. Not at all. Okay, not at all. I'd rather you be able to figure it out. There is one question in your check and reflect questions assigned yesterday, due on Monday, that's like this. I can't remember if it's wires in the same direction, opposite directions, or maybe it's they talk about it being attracting or repelling, and you have to figure out which way the currents are going. I can't remember, but it's like this. So when you see that question later on in those homework questions that I assigned yesterday, due for Monday, I want you to think like this. You got that? Okay, think like this. All right. Number 4. This is kind of going back to some older stuff now. A few weeks ago. An alpha particle is projected at 5 times 10 to the 5 meters per second perpendicular, again, that's good, to a uniform external magnetic field. The strength of the magnetic field required to suspend. There we go again. We're talking about suspending something, but this time it's suspending a particle as opposed to suspending a wire. So this time we're once again going to say Fm is equal to Fg, but instead of ILB, it's going to be QVB. Because again, it's the magnetic force on a particle rather than the magnetic force on a wire. We're trying to solve for the value of the magnetic field. So let's rearrange this. We get B is equal to mg over QV. We plug in our numbers there. And when we do plug in our numbers there, mass of the alpha particle on our data sheet, G is 9.81, Q 3.2 times 10 to the negative 19. And V, the speed, is 5.4 times 10 to the 5. We end up getting a value of B of 3.8 times 10 to the negative 13 Tesla. Now, do we know I'm right? Do we know we're right when we see that answer? No. Hey, but there's a pretty good indication that I'm on the right track with this, right? When you look at the way they want me to express it, they say A decimal BC times 10 to the negative CD. Not only do we know it's a negative exponent, which we got, but we also know it's a negative 2-digit exponent. Okay? Could I make a mistake and still get a negative 2-digit exponent? Sure I could. Okay, but odds are, if I get a 2-digit negative exponent, I've done this right. How would we express that? 3813. And finally, number 5. says a certain charged particle moves in a path of radius 2.5 times 10 to the negative 1 meters. Magnetic field. The speed of the particle is doubled. The magnetic field strength is quadrupled. Hey, it's a variable value changing question again, right? We've seen these questions a lot. We did not see it on our little mini assignment that was due today. Okay, but there's a good chance we'll see it on our test for you guys Wednesday, for the other class on Tuesday. If we don't see it on Tuesday or Wednesday for you guys, then we'll definitely see it again. Okay, variable value changing is not done. You'll see it again. We're talking about the radius of the path of the charged particle in the magnetic field. So we're going to say Fc is equal to Fm. And we're going to say mv squared over r is equal to qvb. We're going to cancel out one of the v's, and we're going to rearrange this to solve for r. I get mv over qb. This is my original radius now. Okay, my original radius, mv over qb, and its value is 0.250 meters, or 2.50 times 10 to the minus 1 meters. My new radius, I got to make some changes now. My new radius, still m, because we're not changing the mass of this particle, but the v is doubled, so it becomes 2v. Charge stays the same, but the magnetic field strength is quadrupled, so it becomes 4v. 2 over 4 mv over qb. Hey, we know what this is. It's 0.250. So that means the magnetic field, the radius here would become 0.125 meters. Now, we want this expressed in scientific notation. So we're going to express it as 1.25 times 10 to the minus 1 meters, or ABCD, 1.251. Now, little word of caution. I could absolutely see in a question like this, they phrase it exactly the same way, except at the end, they say, the new radius is A decimal BC times 10 to the negative D centimeters. Okay, that would be a nasty little trick to throw in, but I could absolutely see the diploma exam people doing that. Okay, pay attention for units. When you see something non-standard like centimeters, circle it. Okay, each question on your diploma exam, hey, next year they get a bit of a break. But for you guys, each question on your diploma exam is worth 1% of your overall Physics 30 mark. You would hate to do this question right, have them ask you to express the answer in centimeters, but you just miss that and express it in meters and get 1% off of Physics 30. Go to a 79 instead of an 80, or a 69 instead of a 70, or a 99 instead of 100. So pay attention to things like that. We only have a couple minutes left in class after the quiz, so what we'll do here is spend 5 minutes reviewing what we did yesterday, the last topic of the unit. We'll spend part of that couple of minutes actually taking us back to something we did early on in the unit to try to tie a couple things together here. If you remember early on in the unit, we learned about a discovery made by a guy named Ørsted in the year 1819. Yesterday, we learned about a discovery by a guy named Faraday and another guy named Henry in the year 1831, only 12 years later. And then we learned about this other discovery, this third discovery, which is really just a combination of the first two, we call Lenz's law. Ørsted's discovery in 1819 said that an electric current generates a magnetic field. That's it. Okay? There's no conditions attached to that. If you have an electric current, you have a moving charge, it will every single time generate a magnetic field. Now, we can find the shape of that magnetic field. We know it's always circular. We can find the direction of that magnetic field by the wire-grasp rule. In this case, it would be counterclockwise. We always have a magnetic field. No conditions attached to it whatsoever. Yesterday, we learned that the opposite can also happen. A magnetic field can also generate an electric current. If I can generate B, then B can generate I. But there's conditions attached to this one. You got to have one of the following two conditions met. Remember, you got to have a magnetic field and you got to have a wire. If we have one of them move, either the wire or the magnetic field, then you're going to generate an electric current in the wire, right, Cole? Doesn't matter which one you move, okay? Here's the wire, here's the magnetic field. I move the wire. Good, current generated in the wire. Move the magnets. Good, current generated in the wire. Move one of them, generate a current in the wire. The other condition that could be met, and remember one of these two has to be met, once again, we've got a wire and a magnetic field. We can change the magnitude of the magnetic field. So increase its strength, decrease its strength. Either one of those conditions will cause a magnetic field to produce an electric current, which is the exact opposite process of what Oersted discovered 12 years earlier, that an electric current generates a magnetic field. The third thing, and this is what we talked about at the end of yesterday, was this whole Lenz's law thing. Lenz's law says that, look, if you got a wire or a coil or even just a copper tube or just a little 3/4 ring of metal like you saw in your assignment that you handed in earlier today. A conductor, basically. And you got a magnet, a magnetic field, and you move one of them. Okay, then that magnetic field will generate an electric current. That's Faraday's discovery, right? Faraday-Henry discovery in 1831. Nothing new there. If you move a magnet or you move the conductor, you're going to generate an electric current in the conductor. Now, if we take a step back here, that electric current that's generated by the magnetic field will produce a magnetic field. So it's kind of like Faraday and Henry, magnetic field produces a current, and then it's kind of like Oersted, current produces a magnetic field. We got two magnetic fields, though. We got the first magnetic field, the magnetic field that was moving through the conductor, and then we get the second magnetic field, the magnetic field that was caused by the current that was caused by the moving magnet. Those two magnetic fields, B1 and B2, will interact with each other to, what's the word I'm looking for? Not to oppose each other, I don't like that, to oppose the motion of whatever it is that's moving. So if the magnet's moving, the motion of the magnet is going to be opposed. If the wire's moving, the motion of the wire is going to be opposed. In other words, it's going to be harder to move it, right? We dropped the magnet yesterday through the copper tube. It didn't accelerate at 9.81 meters per second squared because its motion was opposed. In other words, there was a downward gravity force acting on it. There was an upward magnetic force acting on it, opposing it. Now, gravity still won because the magnet still fell, but gravity didn't act as strong, didn't have as strong of an effect as it normally would because of that opposing force. Okay. How does that kind of manifest itself in some questions? Well, we saw this a couple of times in our mini assignment, right? Let's say we've got a coil like this. We don't need a core inside that coil. You guys see what I'm trying to do there? Kind of go up in the front and then down in the back. My dotted lines represent kind of in the back. See that? Instead of attaching like a battery to this, maybe I attach a light bulb to it. A light bulb, there's not even a battery. How's the light bulb going to light up? Well, it isn't right now because there's no current in this right now. It's just a wire. But if all of a sudden I take a magnet, maybe a south pole and a north pole right here, and I move that magnet towards it, what's going to happen? Well, now I got a magnet moving relative to a wire. That's electromagnetic induction. That's this, right? Faraday-Henry's discovery, electromagnetic induction. That's going to generate an electric current in that wire. Which way is the current going to go? I don't know right now. Okay, but what I do know is that current will produce another magnetic field, which together with the first magnetic field will oppose the motion. So what is the magnetic field going to look like in this coil as a result of that? Well, it's got to oppose the motion. So this end has got to be north and this end has got to be south. Does that make sense? If it was south and north instead of north and south, then it wouldn't oppose the motion at all. It would help the motion. Now, if we wanted to, we could actually figure out which way the current is going in this as well. Let's take our coil that we used way back when we did the coil rule, wrap it up like this, and say, all right, look, I know my thumb has to point from south to north inside the coil, right? Because that's the direction of the field inside the coil. So thumb goes from south to north. Thumb goes towards the left side of the page. In front of the wire, in front of the coil, when my thumb goes toward the left side of the page, my fingers point down. That means the current that's induced here by this, it's not caused by the battery, because there is no battery. The current that's induced by this moving magnet is going to go this way, down in the front, up in the back, down in the front, up in the back, and it's going to end up going around to counterclockwise. That make sense? I think you saw a question in your mini assignment. It was kind of something like this. I don't remember exactly what it looked like, but we didn't really have anything there. There was just a gap. And the question was, which way does the current go? And if it goes, let's say this is X and this is Y. Well, in this case, it would go from Y to X, right? And Y would become positive or negative? Positive. X would become negative. And why is that the case? Well, if you're losing electrons here, gaining electrons here, then going to become positive here and negative there. That make sense?